Okay, good afternoon, or good morning, or good night. Let's get started. Today I want to talk about Bitcoin. And the reason I want to talk about it is it solves a hard problem, namely achieving consensus with Byzantine participants. And it solves it. So with Byzantine, I mean participants that might be malicious or adversarial, and it solves this problem in the context of a completely open systems. People can join and leave the system at will, and some of them may be malicious, and yet achieves consensus on the order in which transaction happens. So it does it actually in a very challenging context of actually really doing it with money involved. The design, looks a little bit like has aspects of Sunder. So in the sense, there's a signed log of operations, in this case, transactions. But unlike in Sunder, that actually can handle forks. And so most of the the many aspects that are interesting to talk about with respect to Bitcoin, but mostly I'm going to focus on sort of the distributed systems aspect of this particular paper. This paper is a bit unusual, or quite unusual. First of all, this is not a paper out of the sort of scientific literature that we've been reading so far. It comes out of a different part of the world. It is pseudo-anonymous. And it has a particular gripe with financial institutions, and you can have all kinds of opinions about whether Bitcoin in general and cryptocurrency in general, but from the perspective of distributed systems, this is a hugely successful system. This is really truly an open system that can tolerate the Byzantine participants and achieve consensus. And so really, the focus on this lecture is trying to, understand how actually to choose that particular aspect. Any questions just before I dive in? Okay, so as I mentioned, the context is here, financial transactions. And so there's sort of free overriding concerns, when transactions are involved or money transactions are involved. First of all, of course, there's the concern of outright forgery. Where basically, people cook up, transactions out of thin air and enter them in the log and, try to mislead other participants, that actually they're spending their own money. While spending somebody else's money. And this problem is reasonably straightforward for to solve, and in a very sort of similar style to Sunder, but basically signing operations make it hard to actually forge. And in fact, so the general setting here, correct, is the same as in Sunder. Well, the Byzantine participant is very, very, very powerful. We're going to be assuming that the crypto systems actually work and cannot be compromised. And so a lot of the core functionality or the basis on which we might conclude that actually things are secure are all going to come down to the fact that the underlying cryptography is correct. So that's one challenge. The second challenge, which is the one that the paper spends most of its time talking about, is double spending. So you legitimately have some Bitcoins that you accumulated, and business participant tries to spend twice that same Bitcoin. And of course, we want to avoid that particular problem. It would be not ideal. And the main ideas we'll see is that there's a public ledger or a public log of all the transactions, so that you can see if the transaction actually, if that money was already spent in an early transaction. and really trying to achieve consensus on what is actually in the log is sort of the heart of the paper. Then, of course, in addition to these two, there's sort of the obvious other problem, which the paper doesn't really talk much about, and we're also not going to talk much about, which is just theft, where somebody actually steals somebody else's private key and therefore can spend money or bitcoins using that particular private key. And it turns out to be in practice a serious problem. People store their wallets with their signing keys on computers. Computers can be broken into, and therefore people can break it or steal somebody else's money. And I think it's a serious problem in practice. I'm not going to be spending much time talking about it. In fact, again, I just want to focus on the distributed systems aspects. Any questions about the challenges? Okay, well, let's look at the transaction then. What's actually in it. So this is basically what is in the ledger. And I'm going to simplify this greatly, because some of the details actually don't really matter to the discussion that we're going to have. And the first order you can just think about it is every transaction is a record, and that record has a public key. Of the user, for which the money is intended. So this is the destination. A hash of the previous transaction, for this particular Bitcoin, and a signature, and we have the private key U2, who is basically the previous owner of that particular Bitcoin, and that's sort of, you can think about this as the source. So basically, U2 is making, granting, bitcoins or transferring bitcoins from U2 to U1, so that U1 can spend them. And of course, there's all kinds of other stuff in it, like there's an amount in it, it's a fractional amount. There are many destinations and many sources possible, many ins and outs. But we're going to basically all ignore it and just sort of focus on this sort of simplified description. Turns out that transactions are encoded also not sort of like sort of passive records, but basically in a little scripting language, and also going to ignore all those aspects. Instead, I want to focus on this thing and talk a little bit, show a little example, so that we get a little bit of handle of actually what we're looking at in terms of the challenges. So I'm going to sort of look at an example ledger and sort of try to understand actually, what it means to be a Bitcoin or what a coin is, because it's not like sort of a single thing. Actually, it really comes down to it's actually sort of a SHA-1 of the last transaction. That is sort of what a coin is. So let's say Y owns a coin and received from X. And so that means that there's somewhere in the ledger, there's sort of a set of transactions that transfer the money or the coin or parts of the coin to Y. And so let's see, like somewhere maybe there's an entry in the ledger somewhere in some period of time where X actually received some Bitcoins, and now it sort of grants it or it has given it to Y. So there's another transaction in the ledger that basically records that fact. And so that might have the public key of Y as the destination, the hash of the transaction 6. So that uniquely identifies a shorthand handle for actually uniquely identifying transaction 6. And so we have the ledger or record that we think is transaction 6. And then we can recompute the hash of that transaction compared to the one that's stored in transaction 7, and truly determine that basically transaction 6 was the source for this transaction 7, or its base to the previous transaction was transaction 6 for this particular coin, and is assigned by X. Now, so this is sort of a situation where Y obtained basically some bitcoins from X, and now Y wants to spend it. For example, maybe Y wants to buy a latte from Z, and so it's going to transfer some money to Z. So maybe we'll see another transaction in the ledger, which is going to be of the form. This is one that actually Y is going to add. Z hash of the previous coin, which is the last transaction for that coin. So that's T7, and it's sent by Y. And basically, C wants to, before Z actually hands over the latte to Y, C needs to do some verification to make sure that this actually is a legit transaction. So we'll look up transaction 7 and compute the hash of it. Double check that the hash actually corresponds to the one that actually is listed in transaction 8. If the hash checks out, so transaction 7 is indeed we believe that the one that actually transaction 8 refers to. Z looks up the public key in transaction 7 for Y, which presumably is the public key of Y. Then verifies and use that public key to verify the signature of this transaction, and the signature, of course, covers the whole transaction. And if the signature checks out, then Z can be sort of confident that actually the ledger contains a transaction that basically transfers some amount of money from Y to Z. And so at this point, the verification, Z verifies, and if it's okay, whatever, ship the latte, and if not, reject. And again, like before in Sunder and in all these sort of schemes, we're relying here on the fact that basically Y, is careful with its private key. So we have to assume that Y didn't disclose in any way its private key. Because if anybody has this private key, then basically anybody could cook up the signature and is able to spend basically Y's money. Although maybe from the perspective of Z, it doesn't really care. Okay, so that's sort of the basic plan in terms of having a record. And this seems pretty good, right? I mean, there's a record of the transaction that happened. When C receives a transaction, they can check whether this is a valid transaction, and that allows it to decide whether to actually accept the money and deliver the goods. So one key challenge now sort of left, we're sort of seeing that outright forgery is difficult. But we need to think a little bit about the double spending. And so the double spending problem is as follows. Let's say instead of creating one record, as in this particular example in transaction 8, Z actually creates, or Y creates 2 records. One record is basically giving the one that we just saw, our T8, Y to Z with the hash of 7. But let's assume that actually Y also tries to double spend its money, so it creates a second transaction, T8 prime, where the record is basically the same, except the money maybe goes to Q, and it has the hash of T7. And of course, signed by Y, signed by Y. And now, let's say, both Q and Z are latte stores. If, Z accepts T8 as it would, because everything will check out, as we saw in the previous slide. Then Z would actually ship a latte to Y. When Q, not knowing anything maybe about this other T8 transaction, sees this T8 transaction, checks out. It's indeed the case that the money in T7 was transferred to Y. The thing is checked with the signature for Y is valid, and it will say, okay, great, I'll thank you for the money, I'll ship you also a latte. And now, so we're in this bad position where Y by double spending or succeeded in double spending and got 2 lattes. And just the problem that basically the paper is really focused on and trying to solve. And the basic approach is sort of similar to what Sander was doing. Let's keep a complete log of all transactions since the beginning of time. And the log contains all the transactions, including the order. Right, and so let's see, so we just sort of put the transactions in, whatever. Here we had T6, here we had T7. So if there's a public record that is ordered of all the transactions, T8 or T8 prime goes first. Let's say T8 goes first, and then T8 prime goes in the log. And if this would happen, then no problem at all, right? Because this was the transaction from Y to Z. This was the transaction from Y to Q. And basically when Q validates, when Z validates the transaction, everything looks perfect. It's exactly as before. When Q validates the transaction, in addition to the checks that we just looked at, it actually looks in the log. Q looks in the log to see if T7 basically was already spent. And of course, scans back in the log, runs into T8, and sees that actually the money has been spent, and so therefore it will reject T8 prime. All right. So that's the basic plan, and so basically we're reduced to one problem, which is like, how do we actually ensure that all participants in the systems actually agree on this log, and that all the transactions are in the same slot everywhere and contain the same content, the same hashes, the same signatures, so that we can actually verify the transactions using the scheme that's sort of laid out on this slide. And so this is where the sort of consensus problem comes in, and sometimes people refer to the solution here as the Nakamoto consensus protocol. Now, before diving into that protocol, I want to sort of sketch out, possible solutions that are not going to work, just to get a little bit of a better sense about what the challenges are that this sort of Nakamoto consensus actually solves. So, design one is not really design; it's more sort of an idea to sort of think about and then reject. Design one, maybe it's the easiest design, is let's assume we have a server S, and the server actually is just trusted. And we have clients, that submit transactions, whatever, T6. Client 1, client 2, whatever, this is X, Y, and Z. And they just submit these transactions to this trusted server. If all the clients trust the server, then the server can just produce a log, right, with all the transactions in it, and order them appropriately, et cetera, et cetera. So if we assume there's a trusted server, then this problem is actually reasonable, straightforward to solve, and if that's the setting that we're in, then we're in great shape. Maybe we'll replicate the server using some Rafna type protocol, and we have a fault tolerant server, And really the only downside to this particular approach is if the clients can just not agree on a single trusted server. And so, for example, in the case of Bitcoin, where you want to do transactions, maybe the rest of the world will not trust the U.S. government to actually implement this server correctly and produce a log. And in that case, with multiple different clients just cannot agree on a trusted server, then this solution just sort of doesn't work. So that's one solution. It's the easy one, but in the case of a decentralized design where the participants don't trust any central component, this is not a workable solution. So now we could consider, using sort of the more Sunder-like approach, modify the scheme slightly and say, like, okay, good, we know actually how to deal with untrusted servers. In fact, we read a paper about it last week. And so let's assume that this server is actually untrusted. And we basically play the Sunder game. The clients produce the logs, read the logs from the server, append their records to the clients append their records to the log, submit it back to the server. And so the server is basically doing almost nothing else than sort of relaying logs between different clients. And we've seen in last week that actual approach works really well. And can be used, but it has one shortcoming, as we saw, namely the server can present two very different views of the world by basically forking the log. So maybe the log has some prefix, whatever T1, 2, 3, 5, 6, 6, 7, but it has T8 in this one and has another log which indeed has T7 and T8 prime. Right, and so one fork, we got our T8. On the other fork, we have T8 prime, and now, like, we can't agree or settle on one particular fork, and the server sort of persistently, keeps the two worlds apart. Like, so Y is Z is in one area of the world, Q is another in the world. Y always gets the first sort of log, and Z always gets the second one log, or actually the other way around. Then they will pretend there's okay, good. Yeah, there was no money earlier spent in T7 in this log, so Q will actually accept T8 prime in this world, and here Z will accept T8, and so Y succeeded in actually double spending. And so this design doesn't work for the particular problem at hand. We need some solution, and this is where the consensus comes in. We need some solution basically for the untrusted clients to basically be able to settle on which fork they are on. Okay, so let's think a little bit about that. So think about a much more decentralized design where we're just going to replace the server with a network of computers. And so this is our. And this goes to gets us closer to the Bitcoin design, where there's indeed a network of peers that sort of all collaborate together to sort of provide this single log. Although even some of the participants actually might be malicious and try to do something different. And so basically, the idea is that when a client actually creates a transaction, then the transaction actually is distributed across a network of peers. In fact, the client one might be a peer himself. And so the transaction is spread around. And every node in the network actually maintains a log and appends the transaction to its log. And the problem that we sort of have left is how to agree on an order. And we actually have seen these kind of sort of systems before. Like, in fact, in Raft, we had multiple computers, and they were able to agree on an order, correct? And the basic trick that was used, or the basic insight, is to basically compute some majority and have a majority of the nodes agree that in slot 6 is going to be transaction T8, and in slot 7 is going to be T8 prime. And and that works great, correct? If we know exactly how many nodes there are in the system. If we know there are 5 nodes in the system, and then the majority is free, and so if we receive a response from free participants, we know, okay, we can commit that particular slot. And the problem really here is that this is a decentralized system that is completely open. The system nodes may leave and come at any particular point in time, and like there is no list of all the participants in the system. So there's also no clear what is a majority in a system like that. Because it's completely open, and so there's like the notion of a majority is completely ill-defined. So we need some sort of like our sort of usual game of sort of doing voting on a majority and then accept the result of the majority is not going to sort of play out. And so the sort of the game, the sort of raft, even though it's a consensus protocol, it's not going to really work out because the setting we're dealing with is a decentralized, open, distributed system, as opposed to sort of a closed system, as in the setting of raft. Does this make sense so far? Let me pause for a second before getting into the more technical part. All right. Okay, so how does Bitcoin solve this problem? And the key idea is something that's called proof of work. Basically, the rule is that there's a amount of work that a node needs to do to actually be able to extend the log. And the basic rule is that the winner in proof of work, the machine that's able to solve the puzzle first, basically decides on the next log entry. And the basic idea that this might, you might actually get some intuition why this actually will work out is because it's basically hard to impersonate the winner. To actually solve the particular proof of work puzzle that needs to be able to add to the log actually requires a real computer, a month roughly of compute time to actually solve the problem. And so if you can solve and demonstrate you solve the problem, you know for sure that somebody actually spent a month of work actually doing it. And this is sort of enough to convince the rest of the system that the real resources were actually spent to be able to append to the log entry. And you can maybe think of other type of schemes of like whatever the unique IP addresses or things like that, but all those kind of things can be actually easily falsified. And so the sort of proof of work idea is sort of the core to demonstrate that I can really put a month effort in to actually to figure out what the next, or to compute, be able to be able to append a log entry to the log. One, just to get that immediately out the way, one downside of this sort of proof of work approach is that it actually wastes energy. And in fact, if you're, Bitcoin has become so successful that a lot of people are mining and doing this proof of work, that the energy bill or the energy consumption of all the combined miners together is incredibly significant. It's huge. And so the complete downside of this approach is the waste of energy. In recent years, there have been other cryptocurrencies or other designs that are based on a different idea. Instead of proof of work, they're actually based on something that's called proof of stake. And this basically sort of the game there is that, like, let's say you own 3% of, the currency, then you get because of your you own 3%, you can actually decide, for 3% of the log entries, which ones are going to be appended. And so there's a completely different approach that doesn't require solving computational intensive puzzles, and it seems to get quite a bit of actually attention, and there are cryptocurrencies that use it, and in fact it looks like one of the more major ones, Ethereum, seems to be sort of slated or going in the direction of a proof of stake approach, but Bitcoin uses a proof of work approach, and so we're just going to proceed with that design. Any questions?
So let's. So I'm just wondering of how it's hard to impersonate the winner. So let's say that we have server A and server B, and server A wants to append entry, let's say E1, and server B wants to append entry E2. Mm-hmm. So server A solves the puzzle and publishes the solution, right? And I'm assuming that the solution is easy to check. So then server B sees the solution and checks that it's correct. So it cannot work that server B just simply republishes the solution with its own name and signing it by its own name, because the puzzle for E2 is different from the puzzle for E1, right?
Yeah.
Okay.
Yeah, exactly. And we'll see, we'll get into this in more detail in a second. Okay. This is sort of the basic insight. It's of course not enough, but it will turn out to be enough to basically settle on a fork. So we're going to accept there are going to be forks, and then we're going to have, because Bitcoin basically accepts that there are forks, like in Sunder, but then has a way of basically deciding which fork to settle on.
I see.
Yeah.
So I had a question about network partitions.
Yep.
And I was wondering how, like, if you were able to make a partition like on the internet, which, it's probably like unreasonable, but you're able to partition the internet, like the whole internet, and couldn't you convince, like, one, so like double spend by like spending on both sides of the partition?
Yeah, the partition never heals. You can succeed.
Like eventually, you'd assume it heals, but then by then, right? Like, you probably would have gotten like something shipped or.
Yeah, so in generally, so we'll see, we'll talk a little bit more about it, but like there are all kinds of, there is ways of creating forks, and what you're describing is basically a fork that persists for a long period of time. And we'll see basically Bitcoin basically produces these blocks with transactions sort of every 10 minutes. And if you're very conservative, or you want to be careful not to be avoid double spending, or making sure that there's nothing was double spent, you generally wait for a multiple of these blocks to appear, like 5, 6, or basically an hour before actually you decide to actually accept to say, yeah, that I'm on the right fork.
Thanks.
Okay, so let's also see actually how the pieces fit together. So it turns out, you don't do a proof of work, per transaction. That'd be crazy, because you got to spend a lot of computational power, for that one single transaction. That will limit the number of transactions you can actually do per second. And so the way actually this is done is that basically transactions are grouped in blocks, and the proof of work is done on a block basis. And so we have our network. The way it actually works is that we're not making a log of blocks, but like we make a log of transactions. We make actually a log of blocks, which are called basically a blockchain. And so here we got our network. We have peers all around the world, and the log is basically a sequence of blocks. And so peers have copies of these. They may compute new ones, append them and distribute them and flood them across the network. And so what is in a block? At a very high level. Again, there are many more details that I'm just going to ignore. It's going to be the hash of the previous block. So, b minus 1. So if this is block 5, this is going to be then, b4, so b minus 1. So the unique identifier of basically the previous block in the chain, the transactions that are part of this block, and then a nonce, which we'll talk about in a second, but this is the thing that is going to play a crucial role in the puzzle, and a timestamp. And this is about typically, we'll see a little bit, but think about this as roughly a megabyte block. So basically, the game is the peers collect transactions, then basically solve the puzzle. And once they solve the puzzle, they're gonna ship the block to everybody in the network. Everybody can check whether the peer actually solved the puzzle correctly, and if the puzzle was correctly, and the transaction check out, and everything, the hashes check out, then they're going to basically accept that block as the next block in the chain. So a little bit more detail. When basically the winner gets to decide on the next block. So we have a new block. And this is basically going to be the proof of work, which is done typically, the party that does the proof of work is called the miners. And we'll see in a second why. And basically the game that we're going to play is that the miner has to compute a hash of this new block for that basically has n leading zeros. So, and the way the miner can do that is basically by changing the nonce. So basically, the miner makes random guesses for a nonce, computes the hash, and checks the number of leading zeros. And if the number of leading zeros is n or larger, then basically that is a block that's going to be accepted. The only way you can think about it is that basically the hash value is below some particular difficulty value. This n can be tuned over time, as we'll see in a second later, to adjust the difficulty. But on average, the amount of work that is necessary, sort of they're targeting is about like roughly a CPU month of computation. And it's not really expressed in that way. It's really expressed in terms of number of hashes you can do per second. But then it boils down to sort of shooting for that kind of number. Of course, a lot of peers, do this in parallel. I think the network is currently around 10,000 nodes. So 10,000 nodes might be, and there might be many more miners. I think there are hundreds of thousands of miners. And they might get lucky, right? And you pick the right nonce very quickly, and some of them actually get it quickly. And so what they're shooting sort of roughly is that that the first one to actually solve the puzzle takes about 10 minutes. And by adjusting the difficulty, the protocol can sort of adjust the time, or the time that it will take to actually compute one of these hashes, and sort of the energy that one has to put into to actually solve the puzzle. And so whenever whoever miner sort of solves this puzzle first, basically gets to spread the block across the network, and basically has sort of about 10 minutes to do so, right? And so one reason that the 10 minutes is there is that we'll take a little bit of time to move that 1 megabyte of block across the many peers that are in the network, and you want to make sure that there's enough time to sort of get the block out to many of the peers, so that you can avoid forks, as we'll see in a second. So before that, somebody else actually, solves the puzzle too.
Professor.
Yeah.
So, does the number of leading zeros that a hash needs to be accepted by a node, is that number like set by each node individually, like based?
No. This is part of the protocol. This is an agreed part of.
Right. But
There's
like
consensus on what n is.
but what I mean is like it's part of the protocol, but like so
But it can change, but it can change
well-behaved
over time.
nodes- well-behaved nodes will follow it, but who calculates it? Is it a central server that calculates this in and sends it out, or everyone?
No. We'll see in a second later actually how it's computed. But basically, what I can give you a hint about like how it's computed. One reason the timestamps are in these things is that like if the time between blocks becomes too low, then the difficulty goes up.
Mm-hmm.
And these timestamps, of course, are validated, using the hashes and all that kind of stuff, and sit in the blockchain. Everybody sees the same blockchain, so they will compute, the same difference between the timestamps, and therefore make the same adjustment in terms of difficulty.
Right.
And this is one of the cool parts, correct, of having a log of everything that's in there. Like if have some deterministic, you could compute any deterministic function of like the content of the log.
Right. Okay. So it would be a deterministic function, but at the end of the day, like if I like try and get away with like sending less than n like zeros, then each individual node in the network should call me out.
Yeah, they will reject your solution
Yeah.
because you don't have a real solution.
Okay, thanks.
So what stops an attacker from just constantly flooding the network with wrong solutions?
The denial service attack. Hopefully turns out that the checking the solution is very easy, correct? And so it's easy to quickly reject an incorrect solution.
Thank you.
And how are the timestamps determined? Does each block set the timestamp on its own, or?
Yeah, no, the miner that successfully mines, sets the timestamp in the block.
And what if they just set the timestamp to be like longer than it took, so that it becomes less difficult?
Well, they can't lie too much, correct? Like they have a 10-minute window, sort of roughly, to lie. I don't really know exactly how the timestamp is checked. I don't know.
Okay.
But I imagine it is solvable. Okay.
And how peers get like the transactions that want to be appended to the block?
Thank you. That's the next slide. So blocks and transactions. So let's assume like there is some, block B5 that already has been computed, that sits in the log, points whatever to B4. And so we're a miner, we're working on, we got a block with, that is sort of we're mining on, so that has a bunch of transactions, and we're basically, trying to compute, the solution to this puzzle. And so new transactions come in, right? They arrive. And so the new transactions actually, they call the memory buffer or buffer. They go in some buffer. And basically they're going to, when the next block we're going to be, so at some point, this guy, let's say this is one miner I. So let's say miner I is the lucky one, actually miner I computes, the new B6. And so at some point, B6 is the new next head of the log, which contains a bunch of transactions. And so while, sort of miner I was actually trying to hash, computing many hashes to actually solve the puzzle, new transactions come in. And so as soon as the miner I is done, with B6, it basically selects, the number of transactions, puts a new block together, a partial block. It's not the one that is solved yet. Puts transactions in from the pool, whatever updates, whatever information needs to be updated, and then starts hashing on that one, and hoping to solve it so that can be added, to the transaction log at some point later if it succeeds. Of course, if somebody else succeeds in solving producing B7 before miner I, miner I is going to switch, to the B7 of that block, remove any transactions that ended up already in B7, and continues with the transactions that are left and that are not in B7 yet. Okay, so that's sort of the plan for how transactions and blocks interact at a high level.
So as transactions come in, like, you're trying to calculate the nonce for a block, that'll like give you like, n leaving zeros. New transactions will come in, right? As you do that.
And they're not part of that block. They're going to be sitting on the site, therefore the next block.
Okay.
And
Could you add them to the
that
block?
would change the hash.
Right, but I mean, you just need to keep trying to get like a valid nonce, right?
Well, like, you also have there's a limit on the block size. The block size can't be bigger than some particular predefined constant by the protocol. There's a bunch of other reasons. Once you filled up the block, with your transactions, you keep going hashing until you find the solution.
Okay. Or you get
or you receive a new one and then you reject and you go work on the next one.
Okay. Thanks.
So when someone when a miner like loses, and do they like is it possible for a miner never to make profit out of this because they keep like losing because they don't have enough computation?
Yeah, absolutely. If I would start mining with my laptop, I'm pretty sure I would make no money.
And the transaction pool, it is local?
Yeah, every node maintains this transaction pool, correct? As they receive transactions from other nodes in the network, they keep that transaction pool, and they use that transaction pool basically to fill the next block.
So you want to
And
tell
there are all kinds of rules, like in how you should select transactions, which I'm not going to talk about.
Okay. So to append, you need to tell your transaction to everyone.
Yes.
Okay.
Or you tell to a bunch of peers and they will flood it for the rest to the rest of the network.
So from my understanding, when a miner successfully mines or verifies a transaction, they get rewarded because they did this verification. But they can also lie when it comes to the timestamp. So let's say that you have two verifiers and they're both working on the same block, and they almost simultaneously verified at the same time. But one of them was, they lied and they made the timestamp a bit earlier. So kind of they.
But the difficulty is chosen for a period of time, like for the next 20. There's a whole bunch of series of blocks. It only changes periodically. You can't change it arbitrarily.
So what was that? I'm sorry, I think I missed that line.
The difficulty is not changed on every block. It is periodically changed after some number of blocks have been computed, and so it's done in the back. Everybody can see what these timestamps are. I think it's every I forgot what the exact number of blocks is where when the difficulty is adjusted.
I see. Thank you.
So at that point, you already agreed on all those blocks in the past. So everybody's on agreement on what the timestamps are that we're going to actually use to actually compute a new valid block.
So I had one question about achieving consensus. I guess all of this relies on pretty much every node running the same code, right? Or at least following the rules very, very precisely.
Yep.
What happens if there's a bug in my code, in the code that I'm running? And maybe a bug in a bunch of different nodes. Does that throw off all notions of consistency potentially?
Well, I mean, as long as the majority, as we'll talk a little bit more about it, as a majority of the nodes actually runs the right code, everything should work out.
Right.
But if there's a trapdoor in the code, yeah, you got a problem. If there's a trapdoor in Linux, you got a problem too.
So does every node run the same code, or are there different?
No, there are a couple of different Bitcoin versions around. We'll talk a little bit more about it in a second. But there are sort of the main, core, they're called, and they're like, it is like an open source project, like Linux is, it has maintainers and, code review and all that kind of stuff. And most of the wallets and most of the sort of the peers will run, one of the standardized version, basically.
Thanks.
Okay, forks. So we know now like what the rule is, who can actually extend the log or the chain, the blockchain. You can still have forks. Okay, because use our chain, B5, B6, and we, somebody two might actually get sort of lucky and sort of roughly compute, B7, two B7s at the same time. So here we got B7 prime, and here we got B7 double prime. And that would be problematic for us, right? Because maybe one of these, this chain has the transaction, the Y2, whatever is it, Y2Z. Yeah, and maybe this one has the Y2Q. Right, and we want to sort of make sure that we actually settle in the end on one chain. So there's two reasons why these chains might develop. One is the people or participants find the nonce at the same time, or roughly at the same time. And the second one is that there may be a slow network. And so a peer might receive from two nodes that are in different ends of the network at some point these two new solutions. And basically, when a node ends up in this situation, it basically does nothing. And just sort of keeps the fork around and just waits to see which fork gets extended. And so, maybe this fork, the bottom one, will get extended with, B8. And then the rule is very simple. The peer switches to longest fork. And so basically, all the transactions, that might have learned about in this fork, in the top fork, are just going to disappear. They're going to not matter in the system because in the end, all the sort of good nodes will actually agree on the longest chain and basically proceed, mining along the longest chain. That's the basic plan. And so let's look a little bit about like how would that solve our double spending problem.
Wait, I have a question on the previous slide.
Yep, I'm going to continue on the previous slide and this slide, but
Oh, okay. So
but let me ask the question.
so even if in the second cause, like the slow network, can't you detect that if the miner included the timestamp where when they found the solution?
Okay. You might, already be suspicious or may agree on what actually the next, what probably the right chain is, but it will be confirmed later by future blocks. And you use the future blocks to really decide what the longest chain is.
Okay.
Okay, double spending. So let's talk about sort of two cases. The first one is easy. Why, since the Y2Z and Y2Q to some peer or to the peers. And basically what will happen, correct, in this case is that if it's a well-behaving peer, you'll see like, hey, two transactions that actually spent the same money twice are just going to reject that. So a peer that receives, is trying to go, or a miner that is going to construct a blog, will actually validate all the transactions before they sticks them in the blog. So this will, this is not going to work. Miner is going to reject, a good miner. Okay, the second, sort of the more interesting, I think, case is basically why, since Y2Z, to some set of the peers, and Y2Q to another set of peers. And maybe the one pool is bigger than the other pool, but it could actually end up in a situation where basically we get the chain like as before, and basically one set of peers computes a hash where that includes y to q, and the other one computes a block that actually contains y to z. And so this looks like a double spending thing. And so if you're Z, correct, like Z was the person that is going to decide whether to accept, this transaction and hand out the latte, what you do is you're going to wait, and you're going to wait until there's a bunch of more blocks that are behind it. So typically it's 5, 6 up to 5, 6. For a very valuable transaction, maybe not for a latte, but if you're buying a car, you really want to make damn sure that you're going to get your money, and that Y didn't double spend the money. And so you may wait for a while until new hashes have been ended, or new blocks have been extended to the blockchain. And once you have 5 or 6, as the paper does some calculations, you can be pretty confident, and you can be very confident that that it's unlikely, for an attacker to basically compute a new chain and sort of overtake, the longer chain. Right? Let's say this is the attacker. The attacker has less computational power, presumably, or this is just the assumption behind this whole paper, it has less computational power than all the good people. And so if the good people have more computational power, it's going to be impossible for the attacker, or unlikely, or negligibly impossible or unlikely for the attacker to basically compute faster and actually make a chain that is longer than the good chain. And so that's sort of the key assumption that's behind all this, among this reasoning. And so basically Z, just has to wait for a while until the good guys have extended the chain long enough that the Z is completely convinced that it's impossible for a set of attackers to actually outcompute the good people. And at that point, Z can just accept the transaction and say like, oh, this is a legit transaction, if everything else checks out, and hand over the latte or the car, to Z, or to Y, I guess.
Sorry, quick question. Who distributes the puzzles?
There's no distribution of puzzles necessary, right? The puzzle is predetermined. The puzzle is you have to compute a hash of the block that has enough leading zeros. So there's no distribution of the puzzle. The only thing that's distributed maybe is the difficulty, but as we talked a little bit earlier, that's sort of adjusted over time in a deterministic way.
Thank you.
So there's all these transactions that are happening, and then through some gossip protocol or something, the transaction is distributed to all the nodes, and then somehow there's agreement on what set of transactions are packaged into a block. So everyone has agreement on what the block is before they compute the.
No. The miner receives transactions, correct? We go here. Where was it? New block. There was some slide on.
I think the next one.
Yeah, blocks and transactions. So the miner, basically miner I, just receives transactions over the network, and it just decides which transactions go in that block. And it starts computing, and if it wins, that is the transactions that go in that block.
I see. Okay.
And so that determines then the total order, correct? The total order is determined by all the previous blocks, plus this new block, and within the block, basically miner I has decided what goes in. And there's some complicated rules that miners are supposed to follow, but basically the miner gets to decide.
Thank you.
And there's sort of incentive systems for the miners to do the right thing. So let me actually talk a little bit about this. So far, we've seen this puzzle that's sort of the core of this proof of work idea too, is that's at the core of actually achieving consensus. But this requires the miners actually to do quite a bit of work. Like they have to hash, you have to have a serious computer. It's a month, sort of roughly a month of work, right? And so why would a miner do that? And so there's an incentive system to encourage miners to actually play this role. And there's a rule that basically there's a bunch of sort of Bitcoins reserved in the pool, like when the first Bitcoin transaction was created, and miners get paid or rewarded out of that pool. And so basically the first transaction in a block is basically a reward for the miner. And so basically the miner can insert a transaction in the first transaction in the first slot, where that basically lists the miner's public key and transferring money out of the pool to himself or herself. And that is the way the miners get actually get basically sort of a return or a reward for actually the work they do. That reward changes over time. Currently, I think for today, I think it's 6.25 Bitcoin to actually mine a block. But as it changes over time, it actually has sort of a halving rule that reduces half the, like a couple of years ago it was 12.5 Bitcoin. In a while will be whatever 3 point whatever the half of 625. And I think if I remember correctly, every 210,000 blocks, that number halves. It's until it runs into the most finest, the finest Bitcoin denominator, and then it basically stops. But we're a while away before that actually is the case. If that happens, then the idea is that to mine actually block, every transaction pays a little fee. And the miner collects the fees, from all the transactions in the block, and rewards the miner with those fees. Even now, there are some fees, but to basically ensure that basically the transactions are not frivolous, so really the miner actually earns not only the 6.25, but also like the fees that actually go along with the transactions. Okay, so that's the miner incentive. Bitcoin has gotten so successful that basically there's sort of an arms race in miners. And this is like, for example, why if I would want to participate and actually win and make some money, I'm going to lose because the serious miners are much better at computing hashes at a very high rate than your standard laptop can. And so there's a couple things that are actually going on in this arms race. First of all, the miners form pools. So the basic idea is that the miners collaborate with each other and they share the revenue with each other. And so, like, if you have a pool with many nodes, maybe from different people, many computers from different people, the people can share sort of the revenue stream out of mining. And because they do it as a pool, they're more likely to actually win once in a while. And, of course, probabilistically, they have some chance to win. And then basically, spread sort of the income stream in a more stable form across all the miners in a single pool. And if you look online today, there are some really large pools. And I think like the 3 biggest pools contribute more than 50%, sort of the mining power.
Sorry, why? Is this why you said that each block takes like around 10 minutes to mine, even though it takes a month of CPU power?
Oh yeah, on average is a month, but you're going to have some lucky. You pick the nonce. You can get lucky and actually pick a nonce that actually allows you to solve the problem much quicker. Right? There's always some probability. The nonce is some big number, or And if you pick the right number, you can get lucky. And if many miners do that, there's actually a chance that it's going to take much less than a month. And in fact, that's where the 10 minutes comes from.
Wait, so is the month more important or the 10 minutes more important? Because if there was only one miner, right, and the expected is 1 month, on average it would take 1 month, right?
Yeah, but the assumption is there are many miners.
But wouldn't it vary? If there's a lot more miners,
It's
there's a higher probability of.
Yeah, there's a lot of variation, but on average it's 10 minutes. So it's picked that is on average it comes out to be 10 minutes.
Okay.
Is it ever possible that a puzzle is impossible?
No, I don't think so. It may take a long time. I mean, there is going to be you get to pick the nonce, correct? And there's going to be a case where the hash is going to fall within the n leading zeros.
So since the value of Bitcoin is actually very, let's say, volatile.
Yes.
And so then how can we actually ensure that the incentive system for the miners is still adequate to keep this thing going for the future? I mean, since the number of the reward is predetermined, let's say to be 6.25 Bitcoins, what if for some reason the Bitcoin value just dropped and then the incentive is not good enough for the miners? And so if
there's absolutely no value for miners to do this, then, the Bitcoin network will collapse. And presumably the way this is going to work out is that the transaction fee is going to go up.
But then if the transaction fees go up, then it will be a counter incentive for people who
to use Bitcoin. Yeah, but if everybody's on the Bitcoin network, if you want to trade goods, you have to deal with somebody on the Bitcoin network. So there's all kinds of sort of complicated analysis that I'm not going to predict on what is going to be the outcome.
I see. Okay.
So I guess we're seeing 2140, and that's sort of the point where I think the reward system runs out, and it's going to be all based on transaction fees, and with the current rate.
I see.
Okay, so the other thing that's going on is, people build special hardware. There are companies that, will deliver you boards, that are really good at fast and hashing. And these are, of course, used by the miner pools. People try to, they have high-speed links to many peers, so that if they find a block, they can actually, get it out first, and so they win, et cetera, et cetera. So this is if you're interested in this, you can read lots and lots of information about it online. But still the system seems to be sort of hanging together. Okay, let me talk a little bit about a whole bunch of sort of practical issues that I sort of ignored, although we touched on it a bit. So first, 10 minutes. I think the 10 minutes is basically sort of the time, the sort of an upper bound, where if you will, sort of 10 times the time roughly to flood the network. So Bitcoin wants to try to avoid, these sort of frivolous forks, where basically, two nodes at the same time roughly compute and therefore extend, the chain roughly at the same time. They want to try to avoid that. And so one way to avoid that is to basically give enough time to the nodes to sort of get the block out, to many peers, so that most peers actually know about it. And that, so that's where the 10 minutes comes from. Of course, the block size determines the number of transactions per second. The block size is roughly a megabyte, and so if you're going to do one block, per roughly 10 minutes, then the number of transactions is limited to the number of transactions that fit in a single block, and that is the number of transactions you can do. And it turns out that for today, that the number of transactions is like in the thousands per second. If you sort of work out the numbers, that's sufficient. For example, it's probably the analogy that people always make, sort of bigger than the sort of Visa network, more transactions than Visa can process. But presumably, it's not big enough to actually, basically run all transactions, money transactions in the world across. Another sort of big, I'll come back to this in a second. Another sort of big issue is that changes, to the protocol, require consensus. And in some cases, this is easy, right? Some changes are easy. If one easy change is, for example, the number of leading zeros. There's basically a deterministic algorithm to compute from the past log entries what the difficulty is going to be for future puzzles. And since that is a deterministic function of the log, there's nothing, that changes basically and easy. And there's a bunch of other parameters in the protocol that have that kind of flavor. Some changes, however, result in a soft fork. We talked this a little bit about. Let's say the main software, the main distribution, the core distribution for Bitcoin wants to make a change that there is sort of incompatible. Then you're going to have old clients, clients running with the old software, or peers running with the old software, and new peers with the new software, and that will temporarily may create some forks. And of course, there's some communication going on, and in the long run, probably the people will settle on the new fork with the new software. Some changes actually result in a hard fork. Oops, fork. So, for example, there was a couple of years ago, there was a lot of discussion about this block size because some people in the Bitcoin community want to increase the block size, some other people don't want to increase the block size, and basically, they split, and there's correspondingly two Bitcoin forks running. In fact, there's probably more than two. But like that one resulted in a hard fork split. And so sort of an interesting, aspect of this consensus, type kind of systems that, you're going to have these kinds of practical problems that actually can lead either into soft forks or in hard forks if people just don't want to collaborate on a particular fork. Any questions about this?
What happens in hard forks? Like,
you have two different blockchains, and clients have to choose in which fork they want to be.
Interesting.
Or publish their transactions in both. I don't know.
I mean, but you have say I have like a couple Bitcoin. I'll have a couple like Bitcoin in both forks, right? But I can start spending them in either like.
Well, you have Bitcoins in the prefix of those.
Right, yeah.
Right. So, and both forks have the prefix. So
yeah.
you can't double spend your money.
Huh?
Well, so actually, in the case of like when Bitcoin there was a hard fork, and one of the new forks was called Bitcoin Cash.
Yeah, exactly.
All the tokens were duplicated.
Yeah.
But then the value of the tokens, it wasn't like you doubled your values. Like the price of Bitcoin decreased, and then the difference in that decrease was the value of the Bitcoin Cash.
Yeah.
So think of it like a stock split. Like you get more tokens, but the actual value would stay the same because you're just increasing the supply of tokens.
Okay. Great. Thanks.
Thank you. Any other questions? Okay, good. Well, let me summarize them. So basically what we've seen here is distributed consensus with in an open distributed systems with with potentially Byzantine participants. Oops. Let's see, my program crashed. Hold on a sec. So this is the consensus with potentially Byzantine participants. And the thing that actually is being reached consensus on is this public ledger or public log, if you will. And that basically orders all the transactions ever since the beginning of time. And allow people to check, what the balances are of every public key and avoid double spending. And the particular cool sort of idea here is to basically this proof of work idea to determine actually who is allowed to extend the blockchain. Okay. So that's basically all I wanted to say. And so if you need to run and leave, feel free to leave. This is basically the end of this lecture. And anybody who wants to stay and ask more questions, please feel free to stay. On Thursday, there's no lecture. It's a hacking day. As you know, the Friday is the deadline for the final project or lab 4, whatever you'll be doing. So good luck, trying to get that work finished. And we'll talk then. The next class meeting is next Tuesday. Okay, thank you.
Could you talk a little bit more about the proof of stake?
There's sure. I'm not sure I have a ton to say about it. If you want to know any more details, just Google proof of stake. You'll find a whole bunch of different Bitcoin currencies that use it, and I'll tell you, more detail. But basically, the power in the network is proportional to your stake in the network. And the basic idea is that, like, if you own like whatever 3% or 10% of all the Bitcoins, you get sort of to decide 10% of the new blocks. And you're going to have incentive, the higher your stake, the higher incentive is actually is to play the game correctly.
So the profit becomes more deterministic in that case, right?
It all depends on the details of the protocol. Like in Algorand, basically there's a periodical leader, there's a committee election, and then the committee decides on what the next block is, and then there's a new leader and the new committee election, et cetera, et cetera. And many aspects of that are probabilistic and randomized, so that the attacker can win the game. I mean, these protocols are quite sophisticated.
Also, to be able to mine, you have to have all of the log to verify the transactions, right?
Yes. Yeah, so the miners have a complete copy of the log, which is gigabytes.
Isn't that a lot?
It turns out not to be, totally doable for a reasonable computer.
Okay. Thank you.
You're welcome.
This is unrelated to the lecture, but do you think it'd be possible to talk about during the class sometime, like the design that the TAs and that you had for labs 3 and 4, because it was more open-ended. So
yeah, certainly lab 4 is more open-ended. I was not planning to, I don't know if we have time left to do so. First of all, not everybody has done lab 4. And so I currently have no intention to do so, but of course you can reach out in office hours and talk to the TAs and or reach out later to me and we can talk about lab 3 and lab 4.
Sounds good. Thank you.
You're welcome.
So I had a question about like it says on the paper like or rather sorry yeah, once the latest transaction in the coin is buried under enough blocks, the spent transaction before it can be discarded to save disk space.
Yeah, yeah.
Like I understood though that, you know, blockchain never really discards transactions. It keeps like a whole log of all the transactions. So why is this, like, why was this done in practice?
Because to save space on the allow space compaction on the on the nodes and the miners, and so they don't have to keep track of every transaction in the log. You know, for every basically Bitcoin, they have to just keep track of the last one, and
Right.
that's sufficient. And so one way to think about it is sort of like, you know, you could compute a snapshot in time of all the values of all the coins, and then you don't really have to remember the whole past.
Who does keep the whole past then?
There's two things. So one is like, you know, when you check whether a transaction is valid, you know, you scan the whole log. People don't do that. You know, they take forever. They basically build a data structure that is, you know, quite compact and has the last transaction for every unspent coin. You know, you can totally download the whole log, you know, from the, you want to, from the internet, and it is maintained, and nodes store it, you know, to basically, if they lose all their data, they can, you know, compute all the balances, you know, basically from running all the transactions from the beginning of time.
But so like, if people are like, who maintains the whole block, like the whole transactions?
And
Like,
it's replicated everywhere, right? Like everybody who wants to can have a copy of the log.
right. But if most people are doing this and discarding like transactions, like why would someone keep like the whole like?
But this is not good enough to actually keep track of, you know, this allows you to decide whether a transaction was actually happened in the past, but it doesn't allow you to validate transactions. So if you want to validate transaction, you have to keep the past.
Okay. Okay. Thanks.
You're welcome. Any more questions? Okay, thanks.